Welcome to the last video of the spectroscopy unit. This will be the second day of NMR, where we'll learn a little bit more detail about something called high resolution NMR, which gives us a little bit extra detail about the chemical environment. A little bit of chemical humor. I don't get invited to book clubs either. Yeah, no fun. So when we study NMR day 2, it makes sense that you should have remembered your NMR study from day 1, kind of low resolution NMR, but also chemical structures, organic specifically. Same big idea for the previous 4 videos for this unit. The focus today will be on high resolution NMR, which is this bullet point here, which is not in red, but I just circled it for you. Remember, the key to NMR is an ability to look at a molecule and decide or decipher or deduce how many chemical environments there are for the hydrogens. And we've looked at this molecule before. One chemical environment there, another chemical environment there, another one there. These 6 hydrogens are all the same, and then these 3 hydrogens. And so these reds are not equal. These blues are not equal, just ran out of colors in terms of this particular program for making your videos. But the key is remembering those chemical environments. Another thing we'll need to think about is, for example, this hydrogen is bonded to an oxygen, and the atom next to it, how many hydrogens are bonded to the next atom? Here's a carbon that has a hydrogen, this hydrogen. The surrounding hydrogens, how many are there? So we're kind of looking for high resolution NMR. We're not just looking for the chemical environments, but we're looking at the surrounding hydrogens for a particular hydrogen atom, or group of hydrogen atoms, or cluster of hydrogen atoms. The same NMR data in terms of chemical shift that we've already learned, so nothing new there. To refresh your memory a little bit, we did look at in the previous video at the proton NMR, or hydrogen NMR, for ethanal. This hydrogen has an integrated trace of 1 relative hydrogen around 10, and that is the aldehyde hydrogen, which is typically between 9.4 and 10. This CH3 is next to the carbonyl carbon, which might make it a little different than what we would typically expect for a CH3 between 0.9 and 1. This is a little bit higher than that at around 2.3 or 2.2 maybe. But the key here is this is worth 3 hydrogens in terms of the integrated trace, and it's clearly not the same as this aldehyde hydrogen way up here. So this was the low resolution NMR. We get 1 peak for this hydrogen, and we get 1 peak for these 3 hydrogens, all the same. High resolution NMR, we're actually going to get a quadruplet, or a series of 4 smaller peaks sort of within the 1 peak for the aldehyde hydrogen, and then we're going to get 2 peaks kind of within the 1 peak we saw earlier for the CH3. Now we're going to learn what high resolution NMR can tell us in terms of this, and this is called splitting. And in low resolution NMR, we just have a single peak. We had 1 peak there and we had 1 peak there. But in high resolution NMR, we actually have splitting into smaller peaks. And that's what we're going to learn about. So in low resolution NMR, that 1 peak had maybe this particular energy or this particular chemical shift. Well, high resolution NMR, we're going to have 2 smaller peaks that have the approximately the same total combined area as this 1 peak had. We might see 4 peaks, we might see 3 peaks, and we'll learn about why are there sometimes 2 little peaks here, why are there sometimes 3 little peaks. That's what we're going to learn. So let's look at the aldehyde hydrogen first. The aldehyde hydrogen is bonded to a carbon, and next to that carbon is a carbon that contains 3 hydrogen atoms. So if we say n plus 1, where n is the number of neighboring hydrogen atoms, I get 4 because there are 3 neighboring hydrogens. 3 plus 1 is 4. So these 3 hydrogens cause this high-resolution single hydrogen atom to split into 4 peaks. If you want a little bit of detail on that, you can listen for the next, say, 30 seconds to a minute. If you don't want the detail, maybe fast forward to the next slide. But basically, if I have 3 protons in the neighboring carbon, all protons can be aligned with that external magnetic field from the NMR, or all protons can be against the external magnetic field, or we can have a mixture of 2 protons with the magnetic field and 1 against, or 1 proton with and 2 against the external magnetic field. And these arrows represent the spin on the electrons. Now, if that all sounded like I just said yada yada yada, blah blah blah, okay, not a problem. You don't need to know this detail to understand how to use NMR. This detail right here, 3 neighboring hydrogens will give 4 peaks. That's the detail we need to know. So 0 neighboring hydrogens would give a single peak. 1 neighboring hydrogen will give 2 peaks. 2 neighboring hydrogens will give 3 peaks. And those 3 peaks will look approximately like that. 3 neighboring hydrogens will give 4 peaks, and we saw what that looked like a little bit ago. 4 neighboring hydrogens will give 5 peaks. It'll kind of look like that. So if a proton has n neighbors, then we will have n plus 1 peaks. We'll look at some examples of this, and of course together in class as well. So let's go back to ethanal. If I'm looking at these 3 hydrogens, the 3 hydrogens here have 1 neighbor. And because these 3 hydrogens are the same, they're not neighbors to each other because they're all the same chemical environment. So they're identical hydrogens. So if I have 1 neighbor, n plus 1 is going to be 1 plus 1 because there is 1 neighbor, and that is 2. And that will form what is often called a couplet. And we can see it here in this trace. I have 2 more narrow peaks that have the same height. So these 2 peaks mean that there is 1 neighbor. And that next to a carbonyl tends to be around 2 to 2.5, and that's what we've got here. So let's look at a sample problem together and see if we can make some sense of this. I have 3 different peaks. This is 4 peaks, which means 3 neighboring hydrogens. I write this a bit small here, 3 neighboring hydrogen. This is 1 peak, so that means no neighboring hydrogens. And this is 3 peaks, which is 2 neighboring hydrogens. So the formula we use is with n plus 1, where n here is the number of hydrogens, neighboring hydrogens. So let's say this is p. Well, n is p minus 1, where p is the number of peaks, or the amount of splitting. Remember, we call this splitting. So we've got kind of 3 tasks here: deduce the molecular formula, draw possible structures, and then use section 27 to identify a structure which is consistent with the NMR. Empirical formula is C2H4O. So let's figure out the molecular formula. Notice that I didn't give you the mass spec. Maybe there's another way to figure out the molecular formula. Think about it. Pause the video. Well, the relative trace was 2 to 3 to 3. 2 plus 3 plus 3 is 8. So I think based on that we can deduce that C4H8O2 is the molecular formula. Now, yes, it could be C8H16O4, but we didn't study molecules that were that big. So we're kind of taking the simplistic route. Occam's razor, the most simple explanation is the best explanation. Well, if I have 8 hydrogens, the best explanation is that the molecular formula would have 8 hydrogens. So we figured out the molecular formula. Now, you're going to need to pause the video and draw as many possible structures as you can with that molecular formula. So remember, there was C4H8O2. That is our molecular formula. So pause the video, draw as many structures as you can. Just put them in a line, make some branching, figure out the IHD so you know how many double bonds there are. It's possible that it's a ring structure with only 4 carbons, but not likely. Ring structures usually don't happen until we have more carbons. Not 100% with that, but it's more likely a double bond. So I gave away the fact that IHD is greater than 1 or greater than 0, but you could have figured that out. So these are the structures I came up with. I have 6 different structures. Double check your structures against my structures and see if you can figure out where they might be the same and where they might be different. I have butanoic acid, except I put the butanoic acid, I put the acid group on the right-hand side. Maybe you put it on the left-hand side. Same molecule. What if I have a methyl group in propanoic acid, so 2-methylpropanoic acid? What if I had an ester that had, this would be ethyl ethanoate? Or what if I had methyl propanoate? Or what if I had propyl methanoate? Sorry, this hydrogen's a bit small. What if I had propyl methanoate? Or what if I had, this would probably be isopropyl methanoate. This would be a weird name that I'm not even sure I can figure out. But I can draw it. 1, 2, 3, 4 carbons. 3 plus 3 is 6, 7, 8 hydrogens. So I have 6 possible structures. Did you come up with any that I forgot? Now, I need to narrow down the choices to only those molecules which would have 2, 3, 3 as the ratio of hydrogen environments. So go back to your structures. Pause the video and go back to your structures. Which ones are 2, 3, 3? These are the 2 structures that I found that have 3 to 2 to 3 for the hydrogen environments. This is ethyl ethanoate and methyl propanoate. They're very similar structures, but they're slightly different. All right, let's take a look now. I have my 2 structures, ethyl ethanoate and methyl propanoate, and I have 2 hydrogens for the integration with 4 peaks, a quadruplet, which would represent 3 neighboring hydrogens. So my 2 hydrogens must have 3 neighboring hydrogens. My 2 hydrogens must have 3 neighboring hydrogens. So the peak splitting doesn't help us very much. Let's look at this one. I have 3 hydrogens that have no neighbors because there's only a single peak. 3 hydrogens with no neighbors, 3 hydrogens with no neighbors. That's weird. I have 3 hydrogens that have 2 neighbors because there's a triplet here. Triplet means 2 neighbors. 3 hydrogens with 2 neighbors, 3 hydrogens with 2 neighbors. So I just gave you a problem where the splitting doesn't really help, even though we're trying to learn about splitting. It's maybe not ideal to choose this question, but this is the reality of structures. We have to be flexible, we have to adapt, and so let's adapt. Let's make it happen anyway. What can we do? Well, this CH2 is next to the oxygen of the ester, and this CH2 is next to the carbonyl of the ester. So this CH2 is going to be quite different. This CH3 is next to the carbonyl, and this CH3 is next to the oxygen. So pause the video and see if you can figure out the difference. This CH3 is probably not going to be helpful. This peak right here, probably not helpful because it's the CH3. So let's not worry about that. Let's worry about these 2 hydrogens, and let's worry about these 3 hydrogens. Can we figure it out? Well, if I have hydrogens next to the carbonyl, they're going to be between 2 and 2.5. Well, I have 3 hydrogens between 2 and 2.5, and that is next to the carbonyl. So here is 3 hydrogens with 0 neighbors that is next to the carbonyl that's about 2 to 2.5. So that means this looks like that, which looks like this peak. Now let's look at our CH2. So our CH2 looks to be this CH2 next to the oxygen of the carbonyl, which is between 3.7 and 4.8. And that is exactly where this is. And that CH2 is split into 4 and has 3 neighboring hydrogens, which are right here. So the splitting wasn't directly helpful, but it certainly was indirectly helpful to verify that these values from the NMR table match what we would expect. And that means that I would expect this compound to be ethyl ethanoate rather than methyl propanoate. There we go. I've got now just a summary of what I just talked about, maybe written a little bit nicer than what I've got, and so I would propose ethyl ethanoate as the proper structure. We've talked about this international mindedness before. I'm using a database from Japan. There's ChemSpider, and there are some other databases that are very useful for this kind of work. Intensity ratio of the lines in high-resolution NMR spectrum is given by the numbers in Pascal's triangle, a mathematical pattern known independently over 1,000 years ago by a number of different cultures. Why is mathematics such an effective tool in science? And is mathematics the science of patterns? Nature of science, we've mentioned this one before as well in terms of improvements in modern instrumentation, and you've now seen NMR kind of taken to the next level to give us a little bit more detail about the structure. Connections to other topics, this is a summary that we've seen a few times, so we're not going to belabor the point here. As a summary, we've seen this before. NMR spectroscopy allows for detailed structural analysis, especially when coupled with other forms of spectroscopy. Copy and paste, and so yes, I made the same typo. I apologize. NMR spectra give information about the chemical environment of the hydrogens, and then now high-res or high-resolution NMR also gives information related to the adjacent hydrogens. So that can be quite helpful. Thank you for your attention during this video. If you've got questions or feedback, you know where the link is on Haiku, Spectroscopy Video 5. Thanks again. I'll see you in class.